So, hello everyone to today's seminar. It's my great pleasure to introduce Luc Jaulin today. Luc Jaulin is a professor in robotics at the ENSTA Bretagne in Brest in France. And in fact, he's the first speaker who's giving a second talk in our seminar series. But today's subject is something more or less totally different from what he presented in the very first talk. And today he'll talk about a modified twin arithmetic to characterize uncertain sets. Luc, the floor is yours today.
Thank you. Thank you for the introduction. So I wanted to speak today about twin interval arithmetic because I use it, but maybe not as it is done because objective is different. So I wanted to make a talk about this topic and introduce why twin arithmetic is important for us. So I will start with interval function. And let me say that if you have any question, you can, of course, interrupt me. So what is a interval function? And I will start with a thin function and give the definition of what we classically call a thin function. So it is a function which capital F, which take a box in Rn and produce a box in Rm. So we want this thin function to be monotonic. So it means that if A is included in B, so it will be the same in the Rm space. Okay. I want also some continuity. So it means that if the distance, the Hausdorff distance between two boxes, if the distance is small, then the distance between the mappings, the box that are produced by F, will be also small. And also when the width of X is equal to 0, then I want the image by F is also equal to 0. So W means here the width, whereas D is the Hausdorff distance. So it is a thin. What is now a thick function? So I give here an illustration of what is a thin function. It is a very classical interval function, which takes x1 and x2 as inputs, and we use here the classical rule of interval arithmetic. Okay, so now I will give the introduction of a thick function. So it is the same. I mean, I have the monotonicity with respect to the inclusion. I have also the continuity of F, capital F, but now I do not assume that it is thin. It means that if the size of X, the box X, is small, is equal to 0, then it does not imply that the image, the width of the image is equal to 0. So I do not assume this. And here is an example. I still use classical rules of interval arithmetic, but now I have some intervals, and you can see that if X is a point, then the image will be a box. So it is why we call it thick. So in practice, in our application, F has a closed form. So with respect to the classical rule of interval arithmetic, such as this one, it is a closed form. And a thick function will be used to approximate uncertain function, which is maybe not classical Okay, so let me give you just a representation. I have a function f from Rn to Rp, which is painted here red, and I can enclose it in some kind of tube here, represented here. And the image by x, a point x, is by f, it is a point, of course, but by capital F, it will be an interval. So what is a thick function in this, for a representation of a thick function? If now x is a box, then the image will be also a box of Rp, and I represent like this. And of course, it should enclose f of x. I mean all possible value by f, possible f, inside the tube. So here it's a representation. And a representation of what I call inclusion monotonic. I mean, if all are nested boxes, then the image will be also nested. Okay. Now, let me go once I have introduced interval function and thick and thin. What is a twin? So a twin, or I call it sometimes thick interval, because to me it's not exactly the same, maybe due to the representation, but also due to the arithmetic we use. So we have many, I think in the literature, many people such as Nesterov, Sainz, Gardenius, Krenovich, and so on, which has worked with some kind of twin. So what is a twin? A twin is an uncertain interval. So for me, a twin will be represented by, so the lower bound and the upper bound will be inside an interval, a classical interval. So a twin is a set of intervals. So it is a set of intervals such that the lower bound and the upper bound are inside intervals. So it is the definition I will take. And classically, we use to draw the intervals and the twins, we use endpoint diagrams. So I will show it now. So if I have here a point, so it is a lower bound here and the upper bound here. If I take a point here inside this endpoint diagram, it will correspond to a vector. For instance, this one will correspond to the interval 1 and 7. But for us, it will be an interval. So we can understand that everything which is here will not be considered for us as interval, whereas in a model interval analysis, we will say that they are improper intervals, and here proper intervals. Me, I will consider only classical or proper interval. So I will only consider this northwest half plane here. So we can understand that inside this one, if the lower bound and upper, so I can represent boxes, such as, for instance, these boxes. So when I mean these boxes, it has some kind of lower bound, upper bound, and if I try to draw this one, correspond to a set of intervals. So A here, A, this one, can be represented as a lower bound inside this interval and upper bound inside this interval, and it is what I represent here. So if I take this interval like this, if I call it A, I can say that A, this classical interval, belongs to the thick interval A. Okay. Now we can understand also that for some of kind of boxes, I can introduce some non-proper interval. So me, I consider not as inside the twin, painted orange like this. So it means that the lower bound and the upper bound for B may intersect. Yes? Oh, okay, I continue, otherwise tell me. So what I wanted to show here is that there is different way to represent a twin. I can represent like this with a lower bound and an upper bound. So it means that it is some kind of interval with respect to the order relation like this. So this order relation means that this interval is smaller than this one because its lower bound and the upper bound are smaller than the upper bound and the upper bound for the other one. But I have also some other order relation, such as, for instance, the inclusion subset. So in this case, if I consider this order relation, this box can be represented as the lower bound and the upper bound. It means that this interval is included inside this interval. So that's another way to represent. And I will also consider some other way to represent these twins. So I come back here to my slide. Okay. So different way to represent twin, either with respect to the order relation smaller than, or another order relation subset. But also I can represent by the interval corresponding to the lower bound and the upper bound. So we have chosen option 3, and I will try to tell here what it means. Okay, so it is this picture. So here, if I want to represent a twin, for instance, this one, I can represent by this interval and this interval. So it will correspond to this order relation. Here, as I said before, I can represent either by this one and this one. So it means that I consider the order relation subset. But if I use this one, then I may introduce some bounds that are not classical intervals, proper intervals. This is classically done in a model interval arithmetic, but me, I want to avoid this. That's why I prefer this one. But another way to represent such a box is by an interval for the lower bound and an interval for the upper bound. So I try to represent this one, for instance. And this is a representation I will consider. So classically, when we deal with twins, we mainly use this representation or that representation. And especially, it's not a problem when you use model interval analysis with improper intervals, but me, I want to avoid this. I will consider only proper interval, and I will use this representation. Okay, so now I will start to consider the arithmetic for twins. And I start with the square. So the square, if I have an interval, let's say this interval, the lower bound is red, the upper bound is green, then the image of this interval is represented here by the lower bound and the upper bound. Okay. So the semantic of interval analysis means that if I consider a point inside the interval x, so this one, then x squared will be inside this interval. Now, if I have here I will represent twins. So by the lower bound and the upper bound, which correspond to this interval, it means that, for instance, this interval, I will call it x, belongs to the twin x minus x plus, this interval and this interval, where x minus corresponds to this one, and x plus corresponds to this interval. So it is a set of intervals. And the image of all this interval will correspond to the lower bound here and the upper bound here. And it is what I want to represent by the x squared. So this one corresponds to the twin x. And what I want the arithmetic to is to represent the square like this. Oh. Okay, so assume, so I will consider an example just to explain how we can compute this, just for the square. So I take an interval for this, which belongs to this twin, and I consider this example. Now I want to understand what we mean by if I say that y is the square of x. What represents this one, and how I compute it. So that's what I will do now. I consider this, and of course, what I can say that the interval -1, 0 is an element, belongs to x. Okay. But I also know that, for instance, -3 and -2 also belongs to the twin x. Why? Because we understand that -1 here is inside this interval, and 0 is inside this interval. So we understand that this interval belongs to this twin. Here. Okay. Now, if I have this, it means that minus 1 due to what I have explained just before, minus 1 0 square, which is equal to 0, 1 if I apply the classical interval arithmetic, should belong to x squared. Okay. Now, in the same manner, if due to this, I have minus 3 and 2 square, which is equal to minus 2, excuse me, minus 2, which is equal to 4, 9, should also belong to x squared. So both should belong to the x squared. So it means, so what I have just means, I conclude from both that the twin 0, 4 and 1, 9, like this, is a subset of minus 3, minus 1, minus 2, 2 square, because I have two elements that I will show later that I have the equality, but I wanted to introduce the semantic. Okay. So now how I can generalize this reasoning? The square is classically defined if I use interval arithmetic by the square of an interval is the set of all x2 such that x belongs to x. I can also have a representation using the lower bound and the upper bound, as explained here. I will also be interested by a closed form for a square or an interval, which tells me that the square of an interval can be computed directly from the lower and upper bound using this formula. So it is the one we will use to introduce the square of a twin. Okay. Now, if I consider again this, the same example as before, I would like to know. Sorry, yeah, no, okay. So I want to know how we can compute the x squared. So for this, I know that the lower bound is inside this interval, the upper bound is inside this interval. So I will be able to compute the lower and the upper bound for the square of x. How can I do this? Since I have a closed expression for y minus and for y plus, I will write this. But since I know that x minus and x plus are inside this interval, I know that the bound a minus will be inside this expression where I replace x minus and x plus by the corresponding interval. If I apply this reasoning, I will obtain, thanks to the rule of classical interval arithmetic, I will obtain an interval for y minus and an interval for y plus, and I am sure that the corresponding twin with this lower bound and this upper bound will contain all possible x squared. So it means, since I have obtained the same result as before, I know that x squared is a minimal, so it corresponds to the set of intervals which are corresponding to the square. Oh, let me now give a representation in the endpoint diagram. If I take an interval here, okay, the square of this interval will be here. Okay. Okay. So I was able to compute from this lower bound and this upper bound, which are interval for x, I was able to compute the lower bound and the upper bound for y. So if I take many intervals like this here, I will be able to map everywhere inside the magenta zone. So in this case, there is no pessimism. Okay. So let me come back here. How can I compute the square from the lower bound and the upper bound? I can also select like this different zone depending on the sign of the lower and the upper bound. And I do not have the if statements. So yes, I have here if statements, but I can decompose the endpoint diagram in different zones where I can compute the square. And if I have to compute the image of this kind of box of of twin like X, then I will have to bisect depending on the zone where it is, and then to compute using the close. Since all expressions here are monotonic, I am sure that I will obtain the smaller box for X, for the twin X. So just here, just to show how it works in practice, I consider a twin. I decompose as union of twins in different zones where the square is monotonic. And then I am able to compute, thanks to this decomposition, the smallest twin which contain the square of X. Okay. Okay. Now I will try to say what is the difference with classical twin arithmetic, so to my knowledge, because there is many, all of the different way to understand this. So for us, in our semantic, if X is an interval, then if I use classical interval arithmetic, I know that X squared will belong to the square of the interval X. But now, if the interval X is inside this twin, then the square of this interval should belong to the square of the twin. So it is this line which tells us our semantic. All of them are classical interval. We do not have here improper intervals, such as in model interval arithmetic. So it means that if X here is degenerated, so it means it is a simple interval, then the square will also be a classical interval. Okay, so I hope you can understand all what I explain. Why the objective of twins, different twin arithmetic are different. Here I try to explain what we want to do with a classical twin interval arithmetic. I have a function f, which is considered as known, and I have an interval or a box for x, a box because I am in Rn. So the image, so in the picture, of course, everything is represented as R here and R also in the y axis. So if here I consider an interval, the image of this interval, so we call it the range, I call it here f of x. So this range, we want we can enclose it like this. So by what we call by this magenta interval, we can enclose it quite easily using classical interval arithmetic. But what we want to do with twin arithmetic, classical twin arithmetic, is also to have an inner approximation. So I want from x to have some kind of twin, so that I know I have some idea about the pessimism I am doing when I use classical interval arithmetic rules. Here it is different. What I want to do is the image of x using classical interval arithmetic will represent it here as some pessimism. But what I want to do is not to find an inner and an outer approximation of f of x, as explained before, but of this interval evaluation. So I represent, so I want to find here a twin, so lower bound red, upper bound green. So I want to compute an interval which encloses this interval evaluation. So it was a view in R to R, mapping R to R. But if I try to see in a higher dimension, I have a box X, and if I compute the image by a known function f, I will be able to draw it like this in green. If I use classical interarithmetic, I obtain the blue. So there is some pessimism. If I use twin arithmetic, usually I obtain the red. And the magenta is exactly the one I would like to compute in ideal situation. And using classical twin arithmetic, I will be able to have an inner and an outer approximation, like this. For me, so here, if I have a twin, so with a lower bound and an upper bound which are uncertain, I will be able to compute the red and the green corresponding to the an enclosure of the upper bound and the lower bound, and I will be able to enclose the magenta. And it is what we classically want to do with modal arithmetic or twin arithmetic. For us, it's different. I have X. Here in blue, it is the image by my sig function, which approximate f. And me, what I want to approximate is the blue, not the smallest one, the blue, because it is the knowledge I have on f, which is considered as uncertain. Okay, so let me go to modified twin arithmetic. And some definitions are quite similar to what is proposed by Gardenay, Sainz, and it's quite similar. So I consider here, but it's different because the representation is different due to the order relation I took. And after, mainly when we combine them, it is also different. So let me consider here odd operators such as plus, minus, or so on, a binary operator. I will consider the operation on all possible intervals, and I will take the smallest twin which contain this set. Okay, what is the definition? So from this definition, I am able to get a rule for the plus, minus, multiplication, and so on. You can see that I take the classical operation of interval arithmetic, but I replaced the computation of the lower bound and the upper bound by the corresponding intervals. Okay. Now, if I have a function such as the square, the sine, I will focus on the square, but I can be the same for all other type of unary operator or function, classical function. So I will take the set of all possible intervals by f, like this, and I will take the smallest twin, which encloses this set. So, for instance, for a very easy example, if I take a twin, which is A, like this, since the exponential is monotonic, I will have this definition for the exponential of the twin. And for the square, I have, as I explained before, it is given by this relation. Okay, so it is what I have to generalize for all kind of function. So the fundamental theorem, which is similar to the fundamental theorem of interval arithmetic, will be the following. If f is a thick function, so an interval thick function, and if double square f is a corresponding twin extension using the twin arithmetic, and if I take any function which belongs to the thick function, if I take x, which is inside this box, so it means that the image by f of x, belongs to f of x. It is normal because f belongs to capital F, okay? But this interval also belongs to this twin, which corresponds to a set of intervals. Okay, so this property is our main motivation for our twin arithmetic. Okay. So let me consider here a function such as, for instance, this function. Okay, so it is a function which I take a twin, so this twin, for instance, okay, and I compute here, thanks to this function, or if you want this function, I take points here, and I compute the image here by this function. Okay, and I do this for all points. If I do this, I will fill all the magenta zone here, but I will not fill this zone. Okay, so it means that if I take an interval here, I will not be able to find an interval here, which is mapped by this function inside the green zone. If I apply the twin arithmetic on this twin, then I will obtain the red. Okay, so it is an illustration of what we now. If I take NOS, so I can see some pessimism due to this zone, but I still have the smallest one in this situation. But it is not always the case. So I give you another example, which is this one. Now I consider the function, which is to x, I associate x squared, so using classical rules, minus here a square. So I can see that I have now some pessimism to this. So if I take here an interval here, I will, due to the symmetry of the problem, I will reach a point here. So the image by this function, this interval function, of all these twin, okay, it is a twin, then I will get the magenta segment. And the twin interval arithmetic, like this, will introduce some pessimism because it is not the smallest one. The smallest one would have been this one. So this is considered as some pessimism. I still have some wrapping effect in my arithmetic. Okay. So let me continue. I have an online. So now about the application. It is a thick set inversion. What is a thick box first? Not a twin, but thick box. So I change. I could have called it a twin box, but I'm not sure that so we could call it thick box. So I will try to introduce what it means. So a thick box is a set of boxes like this with a lower bound and upper bound. So it is a set of boxes where the lower bound is inside this box and the upper bound is inside this box. So if I want to have some kind of representation of this, excuse me, I get this. So it means that this blue box here, this blue box, belongs to a thick box. So the thick box is the lower bound here is inside x minus, and the upper bound here is inside the other magenta box. So if you want, this thick box contains many different boxes. Excuse me, many different boxes, such as this one or this one. Okay, a lot of boxes. So if I want to try to draw, to paint a thick box, I will use what is represented here by some kind of clouds with a yellow, with a red zone. Okay. So this corresponds in red to what we could call a thick box. It's a representation I will use. Oh, okay. Now I want to explain how we can introduce thick boxes inside an algorithm. So I have a set Y, and a thick function f, which is uncertain, which give a box to another box, okay? And we want to find the set of inverse, the possible inverse. So we understand that since f is uncertain, I will obtain a family of possible set for x. Okay. And I want to approximate it. So let me show how this can be done. I have these rows, or I have here my set for x1, x2. Okay, and I have some kind of function f which is uncertain, but so I will use f. And here the image space is like this: y1, y2. I have the set to invert is like this, for instance. I will call it it's like this. So this is the set y. If I take a point here, let's say this point, the image by f will be a box. Okay, this box can be like this, but it could be, if I take another point here, the box could be like this. Or if I take another one like this, it can be like this. Okay. So we understand that f minus of y, the one I want to characterize, is x. We can say that this one, I will call it, let's say, A, B, and C. A, since the image by A, excuse me, yes, the image by C, f of C, belongs to y in without ambiguity. So for all uncertain function f, I will reach C will be here. Okay, for all possible f, which belongs to f. So it means that f of C belongs to y. For B, it will be the same. Since the image of B will be here, I know that f of B does not belong to y. But now for A, it will be different because A for some f can be mapped here or can be mapped here. So the set of all point A which satisfy this property are called the penumbra. So this y is called the penumbra. So the image, the inverse image by f can be considered. I have three zones. This one will be x subset given here, which correspond to all x that are mapped in y, okay, for all possible f. I have also another one which is represented here, which correspond to this one, which correspond to the set of all points such that the image will intersect y here. And I define the penumbra, let's say here, which is this one, this zone. Okay. Okay. And what will allow me to do is to characterize this penumbra with some inside and an outside. It means that if I take a box like this and I compute by f using thick arithmetic, I may obtain something like this. Okay, so I represent like this with the lower bound. So I take the same color as before, red for the lower bound, and here green for the upper bound. And I know that for all possible point here in here, I will intersect y. So it means that thanks to the twin interval arithmetic, I will be able to find some inner box inside the penumbra. Excuse me. Okay. So what is the pair x subset corresponds to what we call a thick set. Okay, and it is represented here. I have some set represented here in red, and x belongs to a thick set. with an inside and an outside, as the orange corresponds to the penumbra. So the boundary of this red set on the left belongs to the orange set, so belongs to the penumbra. Okay, so now I can explain what is the main algorithm we'll use here. Okay, it is what we call thick set inversion. If I take the red box here, and I will apply by F, and thanks to classical interval arithmetic, I will be able to compute, okay, this one and this one, and I will be able to show that all points here are inside Y. It will be the same for the outside. If I take a box here, I can compute the image for the lower bound or the image for the upper bound. So this can be done again by classical interval arithmetic. All of them are outside, so I am sure that this one is outside. But for the penumbra, it is different. Look what I was able to do. If I take the orange box here, this one, I compute the enclosure for the lower bound of the image by F, and the same for the upper bound. And this corresponds, what I represent in orange, to a thick box. All thick boxes, which are like this, okay, will intersect Y. So I have some rules that tell me that it is mandatory the case. So I can conclude that this one is inside the penumbra. Okay, so just an illustration corresponding to a localization problem. I have a robot, and it is able to hear some landmarks which emit noise, for instance. So I have 3 landmarks, M1, M2, M3, which are inside some boxes, but I don't know where they are exactly. But the only thing I know is that if I am to a distance lower than, let's say, 20 meters, then I will be able to hear all of them. So I will compute the square distance like this. And due to the fact that the position, so x1, x2 is the position of my robot, and this interval corresponds to the position of my landmarks. They are uncertain. So I have my thick function, and we can understand that the thick function represents the function which corresponds to the model, but which is here uncertain due to the fact that the position of my landmark is uncertain. And from this, I build the twin extension, where I use I replaced by x1, x2 my position by twins like this, and the set I want to invert is given by this box. Since I measure 3 distances, then of course Y will be a box of R3. And if I compute the image using the twin arithmetic, I will obtain this, with the inside in red, the penumbra in orange, and the outside in blue. And the position of the landmarks is here represented by the black boxes. So, so it is a represent. So I know that the set, the family of set, which correspond to the interval set inversion, will be approximated by some kind of interval of set with the lower bound red, the upper bound red plus orange, and this interval of set corresponds to a thick set. Okay, so I have a Python program which is online. You just click here. I don't know if you will see it, but so it is just if I run it, I don't know if it will work, but you can have it by clicking on this link. Normally it should work. So, okay, and you have a representation of the thick set, and you can see the main program is given here. Okay, and inside we use the algorithm, which is not so long. Okay, it's quite easy to understand from the arithmetic. Okay, okay. Where here you can see the square is just here, and for this we use for the interval part we use PyBex. So we use a in Python version of IBEX. So we can just see that it is quite easy to implement as soon as you have a interval arithmetic already implemented, classical interval arithmetic already implemented. Okay, so just the final example, underwater exploration. Okay, I have a robot like this, which is DORAD. We have in Brest. DORAD in Brest, and the DORAD is an underwater robot which is equipped with a sonar. So with a sonar, usually there is we are able to see like this. Due to the antennas that are here, you are able to see some to illuminate under the sea. So we have to imagine that we are under the surface of the water, below the surface of the water. And there is some kind of sweeper. So the sweeper is like here, represented here. Whoop. Difficult to see something. Yes, here is some kind of sweeper. And when the robot is moving, so DORAD is like this. Okay. From above, we have here the sweeper like this. And when it will move, it will explore a zone like this. Okay. Okay, so from the beginning to the end. Okay, so here it is the explore zone. But due to the uncertainty we have on the position of DORAD, the trajectory corresponds to some kind of thick function. Okay, so this trajectory is uncertain. You have different possibilities for the trajectory. So we understand that if we know exactly the trajectory, then this will be, the explore zone will be a classical set. But due to the uncertainty of the position of the robot, we'll have a family of set and we'll be able to approximate the explore zone from the inside and from the outside. So here it will be A plus and here A minus. So it means that the explore zone is a set which belongs to a thick set E minus A plus. Okay, where this one and this one are classical sets, but it is an interval of set. So the trajectory of DORAD is quite well known, but there is some uncertainty. So here I represented two different trajectories which are consistent with the sensor of DORAD. Okay. And if we apply the proposed twin arithmetic, we are able, so we can see here in black here, the trajectory of the robot, okay, the tube for the trajectory of the robot. Here inside in white, we have E minus, and here, if I consider this one plus this one, okay, this one plus this one, it will correspond to A plus. Okay, so the explored zone is between these two sets. So what was possible to solve with our twin arithmetic, if I take a box here, I was able to prove without bisecting them that it was inside the penumbra. So in an algorithmic point of view, it means that I do not have to bisect anymore a zone as soon as I have proved that it was inside the penumbra. So it is an actual experiment which lasts for more than 2 hours, and the distance is several kilometers. I have finished my talk. I'm sorry I was quite long. If you have any question, please, you can ask now. I have a conclusion, but it's okay now. Okay, thank you.
Okay, many thanks, Luc, for your very interesting presentation. And yes, I think we already have the first question. Carlos, please go ahead.
Oh, so stop sharing my screen, maybe. No. Okay. Ask your question.
Wait. Do you hear me now?
Yeah, a little.
Is it better? Wait. Is it now okay?
Yes.
Okay. Perfect. Okay, I think it was a really nice, interesting talk. However, I have a question. It's more about curiosity because I couldn't find the difference between twin arithmetics and an interval matrix. I mean, I just have a matrix and I have two interval sets and I'm going to apply the rest. And this is one of the questions. And the second one should be more related to how determine the lower and the upper interval in the twin arithmetics one again. Because we use intervals because we don't have more information. This is the information that we have. So how do you determine the two sub-intervals that are going to belong to the twin interval? I don't know. That was both my question.
Sorry. So let me first answer to the first question. So if you take, for instance, a matrix, maybe the meaning. Okay. So excuse me. I try to. I will come first answer to the first question. Okay. So for me, as I define a twin interval arithmetic like this, it is a set of intervals. But so like this, it is a set of intervals. So in a mathematical point of view, it is not a matrix of intervals is not a set of intervals. But of course, you can represent a twin interval by a matrix. But you can also say that an interval you can represent by a two-dimensional vector of R2. Okay, you can, but it's not the same. The representation can correspond, but you cannot say that an interval is a vector of R2. You understand what I mean? It is not the same set. One is a set of interval, the other one is not. But the representation in the machine can be very similar. So let me, if you understand my first my answer.
Yes, I think I have the idea. I still don't see completely because I always can arrange a set of scenes like a matrix. And actually, when we start to arrange the scenes, it was okay. Let's build a set, and the best way to represent it is through the matrix.
Yes, I agree. But you can also say that an interval is also a matrix.
Yes. No.
So you can say it, but after you have to introduce some properties. If you consider a matrix, usually it is a space vector. You are allowed to do some operation, and some other you cannot. But in the set of intervals, you can represent it the same way, but the arithmetic you use is different. Now, okay. So now maybe
actually now what I want to know is not now. I just want to read it. Is to compare both operations. How you add two intervals and how I add two interval matrix. So
if you add them, yes, if you add them, you will probably obtain the same thing. But if you multiply them, you will obtain something different. So the operation are the representation can be similar, but the operation are different.
Okay. Now, okay. And regarding the second one,
yes. So,
for example, in your robots problem.
So here, for instance, or not here.
I would prefer the last example that we show the robot.
Okay. Yes, the robot. Okay, the robot. Let me go to the robot. So here it was the robot. This one, yes. So after I got a trajectory, and this trajectory is uncertain, but so I represent by a tube, and this tube here is painted black. Okay. So I did not explain everything, but it can be understood by this previous example. The black, assume that I have we can imagine that I have a robot with 3 times T1, T2, and T3. And the position at time T1, T2, and T3 correspond to the black boxes is not known exactly. And we assume that the robot is able to see around it with a distance of 20 meters. Okay, 20 meters is the distance I have taken for this example. And from this, I know that the robot has seen in a guaranteed way all red points, has maybe seen the orange points, and have not seen at all blue points. So it is very similar. What was able to do is what I was able to do here using the twin arithmetic is to find some boxes inside the penumbra. And this is not a trivial thing to do without the twin in the arithmetic I propose here.
And once again, so what is important, the penumbra?
The penumbra.
In the case of the robot, of the submarine that is
yes,
moving.
Because sometimes people will tell me the robot has finished his mission, for instance, and you want to know which points have been seen in a guaranteed way. You will answer, your interval algorithm will tell you it is a red. Now you will tell me which point I am sure it has not seen at all. It is a blue. And what about what is not inside the blue and what is not inside the red corresponds to the penumbra. But if you try to use a classical interval arithmetic, you will bisect everywhere inside the magenta, and you never know if it is due to the fact that the accuracy is not high enough, or if you can stop bisecting because you will be never able to prove that it is in the red or in the blue. So the algorithm is faster, much faster here, due to the fact that you are able to prove that the box is inside the penumbra. You will not be able to conclude anything about the orange boxes. Maybe they have been seen, maybe not. You are sure of this. For some trajectory, they have been seen, some further, they have not been seen. And the trajectory is represented by a thick function. And this is important, this notion of thick function, to understand the approach proposed here. And a thick function is not, okay, so if I consider classical model interval or twin arithmetics, most of the time they try to solve a problem like this. So they have a function which is uncertain, which is known, the function, which depends on some parameters, and are able to solve some quantified problem like this one. So able to, so these problems are very important also. I do not say that they are very important, but it is not the problem we are considering here. Here we have, for the conclusion, I said that it is different. We consider here, we have uncertain function capital F, and we try to characterize an inside and outside corresponding to these two, to a family of functions which are uncertain and represented by a thick function. I'm not sure I have answered, but
yes, definitely. Actually, you gave me a little bit more. So thank you so much.
I do my best. Okay, thank you.
So, do we have any further questions? So, at the moment, I cannot see a question from the audience, but maybe let me continue with a question. Luc, when you mentioned this, yes, I think the slide, the previous slide that you had with the quantified problem statement could be interesting for discussion.
Okay, where in the conclusion or?
Yes, at the very end, or where? Yes, this one.
I did not. Yes, yes. Go on.
Yes, what you did so far is You started with this thick set y, and you tried to invert the problem, find the interval x.
Yes.
And now my question is, for example, in this, okay, maybe someone is talking here. Maybe you could mute yourself, whoever this is. Okay. Okay, what you did is you tried to compute, yes, the corresponding inputs, the intervals x. And concerning the task of a parameter identification, it would also be interesting to figure out from measured data the corresponding intervals that are consistent with the output and describe the parameters p, for example, the uncertain landmark positions. Do you have any comments on this, how this could be performed?
As soon, okay, so maybe you are speaking about classical set inversion problem. You have some data which are represented by intervals. Yes.
Yes, for example, your landmark positions, and you want to identify this landmark position.
Okay, so I come back here. So if your model is exactly known, so classical normally, when you deal with a classical parameter estimation problem, you have a model, you have some data, and in interval context, you represent the data by intervals. And you want to find all parameters that are consistent with the data bar, with intervals, but you know your model. But sometimes you do not know exactly your model. So you represent your model, which is a function, by an interval of function or by a thick function. And if you do this, you will obtain, using this method, two sets. One, which corresponds to the set of parameters which correspond to your interval data for all possible models, okay? And another set, which is larger, which is the set of all parameters consistent with your data bar, but for at least one model. So if you do this, you will solve a thick set inversion problem. And for this, you will have to use thick interval arithmetic, or if you want, the twins interval arithmetic. So sometimes it's difficult to know how to call it because it's twins, the arithmetic is different, and some people don't want, so sometimes I have the feeling that some people want me to call it twin arithmetic, and sometimes I would prefer to say that it is something different, and maybe to call it sometimes thick interval arithmetic. Okay.
Yes, the thing that you described so far is that you have already information about this uncertainty, for example, of the landmark M1.
Yes.
Is it possible also to identify this uncertainty? This was my question.
Yes, of course. But because here in this example, you can consider here you have M1, M2, M3 that correspond to some kind of parameters. So you can say, I want to estimate my position, but also the position of the landmarks. So if you do this, you will have to bisect in R2 plus R3, so R5 space. It will take time. You can do this. But sometimes you have no parametric version of your model. It is really, you do not want to consider parameters to represent your uncertain function. Because it takes time to estimate these parameters. Sometimes you just want an abstraction which is higher. The uncertain function will be an interval, so a thick function. And if you accept this abstraction, then you will be able to obtain algorithms that are fast because they only bisect on the x1, x2 space. But the notion of penumbra appears.
Okay, yes. Okay. Now it's clear. Many thanks.
Okay, thank you.
Okay, any further questions from the audience? I'm just browsing through the list of participants. Okay, I see no one who has raised their hand so far. if there's someone who wants to ask a question, just please go ahead. If not, I think it's time to close today's seminar. I have, I think, 2 advertisements to make. One advertisement is I'll certainly get the slides from Luc to place it on the web page, and this will certainly be one good option for you also to access the Python code that he had shown, because the link is included in the PDF file, and each of you who wants to play around a little bit with the approach of Luc has access to the source code then afterwards. And the second thing is, yes, usually we have our seminar every second week, but unfortunately I have a collision in 2 weeks with a conference, and therefore the next meeting will take place in 3 weeks. And please be aware of the fact that at least Central Europe is changing time from summer to winter time in the meantime. And yes, I think when you have downloaded also the calendar file from the web page, you should have the correct data. Otherwise, please be aware of the change from summer to winter time taking place in Central Europe. Okay, from that point of view, I'll just wish you a very nice Friday afternoon, evening, and weekend, and see you again very soon in the near future. That means in 3 weeks for the next seminar.
Okay.